Chapter 15, we start looking into alternating current sources. We're going to see how AC circuits behave, and we're also going to take a look at some practical considerations when we're talking about not only the power that comes into our homes, but also how the power is delivered. Let's start with a typical outlet that you might see in a house, an apartment, a dorm, okay? This is what they look like. And as you may know, you have two vertical slots right there with the typical outlet. And then this sort of D-shaped slot, which is at the bottom. Now, the two vertical slots are responsible for sending power and returning power to the grid, whereas the D-shaped slot is actually the ground. So what does AC look like? What does alternating current look like? Well, it should probably be called alternating voltage more than alternating current, but we're stuck with the name that we have. And if we look at the graph right here, where we graph voltage as a function of time, we can see that it alternates from a positive polarity. That means that we have from this starting point to that point right there, the voltage is going to be positive from the hot wire, okay? So this part right here, positive polarity. And then we see that the polarity actually switches to a negative polarity. And for the second half of the phase, it goes negative. So basically, when I plug something in to this outlet, what's happening here is that it's going to receive this voltage that alternates between a positive and a negative. And really, it's not so much that the current flows from one point to another, but the current more or less oscillates within whatever circuit that we have. So let's now take a look in a little more detail how things are going. And again, I just want to make a comparison here. This is DC shown above, or direct current. And we can see that the voltage is held steady and the current is held steady. And we know that from V equals IR, Ohm's law, that as long as the voltage is constant, the current is also going to be constant for a constant resistance. However, with AC, and this is for the case where the load is balanced, we'll talk a little bit more about this later on, we see that the voltage alternates and so does the current, okay? Sometimes they're right over one another. We say that they are in phase, or the phase angle is 0 degrees. Sometimes it's a little bit off for certain elements of the system and for certain circumstances. But basically, we can model the voltage using this function right here, where very simply, the voltage with respect to time, and notice that I've written voltage with a lower V. The reason that I've done that is I want to indicate that it changes with time, as opposed to the amplitude, which I use a capital V, actually use V0. And then we have our sine function, and this is a source of it going positive and negative, because sine will go from a maximum value of +1 to a minimum value of -1. So again, we can see that at t equals 0, the voltage is 0 at 1/4 of the phase forward. Okay, basically where omega t equals 90 degrees, or in radians, pi/2, the voltage is going to reach a maximum. The sine of 90 degrees is 1. The sine of pi/2 radians is 1. Then we get to 180 degrees, and the sine of 180 degrees is going to be 0. The sine of pi is 0. And then finally, down here, we are at omega t equals 3 pi/4, or 270 degrees. And then the whole thing repeats itself over again, okay? Now, for your home, for the United States, it's very important to point out the fact that the frequency of oscillation is 60 hertz. So if you want omega here, omega is 2 pi times f, it would be 6 roughly, 2 pi is roughly 6 times 60, or roughly about 360 radians per second. Okay, so 2 pi times 60 is going to give you your omega there. And that can be plugged into this function right here. And again, you can see how it fluctuates as a function of time. Now, going back to this outlet, this is actually with the cover removed. If we go back 2 slides, we can see here is the protective cover on the outside. Okay, this is all just usually a plastic or metal covering that's going to cover everything up. If we remove that, we can see the rest of the outlet. And the way that this is wired here is that I have my hot wire attached to usually what's a brass colored connector. And then I have, I can't put white on white, but I have my white wire going into the outlet, which is your neutral. Okay, so there's usually a third wire also. It's either copper or it's green, depending on how it's wired. This is your ground, and both the ground and the neutral are 0 volts. Okay, the neutral goes back to the transformer from which the AC changes its voltage, whereas the ground goes directly to ground. And they serve 2 different purposes, even though they're roughly about 0 volts. So again, we look at this, and when we plug a plug in, the neutral prong on the plug is actually slightly bigger than the hot plug on the prong. And you can see the smaller slot is for the hot, the wider slot is for the neutral. And your hot wire, that is what is taking that, oops, come on, give me a box there. That is what's giving you your oscillating voltage. And that is essentially going to be the source of the power going in. Now, of course, the electricity is going to come in. It's going to need to go out someplace, and that's where the neutral comes. Okay, so basically, that voltage can't do anything if it's simply just oscillating without any reference. And basically, by connecting to the neutral, that gives 0 volts to the neutral, where the hot has this oscillating voltage and it's able to do work. Okay. Now, what about what's going on here? Okay, here it's written just a little bit differently with the voltage and how that voltage is changing. Notice we've changed from omega t to 2 pi f times t. They're both equivalent to one another because, again, omega is equal to 2 pi f. But for the United States, our f, our frequency, is 60 hertz. And what that means is every 60th of a second, we are going to see the voltage repeat itself. So 1 cycle is in 1/60th of a second. That's what we've graphed right here. Now, why do we call it 120 VAC? 120 volts alternating current. Sometimes you'll see it written as 110 VAC. It can vary somewhat. Originally, the voltage was set at a slightly lower voltage. Now we boosted it up to 120 volts as a standard. But most appliances can operate safely between the 110 and 120 volts. The other thing that we do get is we do get a little bit of a voltage drop sometimes. This is what my appliance would experience if it were connected right to the transformer. But if you send it through wires, the wires have resistance, and that can lose some of the voltage. So, most appliances will say, as long as you're at 110 volts, you're fine. Now, what does that 120 or 110 volt mean? Okay, it's a little bit complicated, but they're actually referring to the root mean squared voltage. And if you think about root mean squared, what we're doing is we're taking the V, the small v, as a function of time, okay? And we're going to square that and then take the square root of that, okay? I'm sorry, the root mean squared. We are taking, let's do a little better now. We're taking the average time voltage squared, and then we're going to take the square root of that. So what that requires us to do is take our sine function. We're going to, first of all, square it. Okay, so we're going to square it. So that's going to take that negative dip out, right? Then we are going to take the average of that full time. Okay, so maybe you'll get the average right here. And then if you take the square root of that, that'll bring you down to 120 volts. Okay, so RMS means root mean squared voltage. If I took simply the mean, the average, that would give me 0, right? Because sometimes it's positive, sometimes it's negative, and it's equally positive during this phase to what it is negative during this phase. So simply taking the average, it doesn't make any sense. What if I just took the maximum voltage, which for 120 volts AC, it's 170 volt maximum. Well, that creates a problem because when I try to take, we'll talk about this later on, but when I try to calculate the power in AC, I want the power to equal the current times the voltage. And if I take the power of the current times the maximum voltage, I'm going to get the power at this moment, but I'm not going to get the average power that this is putting out. It's more useful to get average power. So instead, I take the RMS current times the RMS voltage, and that gives me the average power. So that's why we do it that way, okay? This 120 is more representative of the power that I'm going to get out of this rather than taking the maximum. And obviously, if I took 0 volts, that would give me 0, okay? So once again, when you plug something into the wall, this 120 volt is actually oscillating around 170 volts, okay? So the highest value that we get here during this oscillation is plus 170 volts. And then, of course, we have negative 170 volts as our lowest, but the RMS, again, is most representative of the power and the energy that we deliver here, okay? After all, when you think about appliances, what are you most interested in? You're most interested in the electrical energy being converted into some other energy, all right? Now, in the home, you do have some of the outlets, okay, specialty outlets, which are designed to take much higher voltages, 240 volts. And we had this discussion earlier. We said that we have 2 hot wires that come into the house, one red and one black. They're 180 degrees out of phase. So at any one time, they are a potential difference of 240 volts. But again, that represents the RMS voltage, okay? That's the RMS voltage. The maximum voltage there is actually 340 volts. So in reality, alternating current actually sends a higher voltage at peaks than the actual rated voltage, because the rated voltage is really the RMS voltage. Now, here we're going to revisit some of the household receptacles or household outlets that we typically see. Most of what is going to be in a home, apartment, or a dorm is going to look like this. It's going to be the standard 15 amp, 120 VAC outlet. And the reason why we shape the outlet like this is because any appliance that uses 15 amps or less is going to fit into that receptacle, okay? And basically this thing is wired such that it's fine with 15 amps, but it's probably hooked to a 15 amp breaker. So if you exceed that 15 amps, the breaker is going to trip and you're not going to get any current through there. Okay, if you look around our labs, our classrooms, you'll see that the outlets actually have this extra little, what would you call it, a wing? But it's T-shaped accepting. And the reason for this is this will accept normally shaped plugs, but it will also accept, I don't know how long I'll be able to draw this, but it'll also accept plugs which have a horizontal and vertical prong. And of course, we have the D-shaped ground here, okay? So what we see here is that the neutral can actually go in the horizontal direction in this particular case for certain plugs. So for appliances that use between 15 and 20 amps, they'll have a specially shaped plug that will allow it to fit into this outlet. And this particular outlet, again, is typically connected to a 20 amp breaker. So if you exceed 20 amps, that thing is going to click off, okay? Now, also, we have different outlets for your 220, okay? Now, 220, I'm sorry, it's 220, you know, it's 240, but it's close to 220. Here, we have a 220, a 240 volt, 20 amp outlet, and it will accept a vertical and horizontal input, okay? If we bump up to 30 amps, both prongs, both the neutral and the hot, are going to be horizontal. And then for higher amounts, the shape will be different, such that the prongs are at angles that correspond to the proper current amounts, okay? So notice for this one right here, you would have a prong, two prongs like this, and then the neutral, I'm sorry, the ground would be shaped like this. And then for this one, this would be this way, this would be this way, and then the ground would be vertical. So this one right here would accept, yeah, I would almost think it would be backwards. So I'm not going to comment on that. But again, different shapes, obviously, for different types of current loads. And oh, this is 120 or 240. Well, that's interesting there. So that's the extent of my understanding on those. I don't want to be foolish and make a remark that doesn't correspond to reality. But again, you can see how this works for different amounts of voltage. And again, here's your 240 volts. It peaks at positive 340 volts and then dips to negative 340 volts. It's also at 60 hertz. So it's oscillating at the same frequency because it's coming from two of the hots rather than one of the hots. But we're basically superimposing the two voltage differences and therefore doubling our voltage there. Here is the breaker box that is distributing current throughout the home, apartment, or dorm. And what's removed off here is the front panel. Actually, there's two things that are removed. Typically, you would have a metal panel that would only show the breakers themselves. Okay, there'd be little punch outs for the breakers themselves. And then there would be a separate door on top of that. All of that's been removed here. And what you see here is basically the two hots. Here you would have one hot and another hot coming in. I don't know why they made this white, but it should be red and black for the proper color right there. And then there would be an additional neutral, which is coming from the pole transformer. Okay, so here, this is interesting to see this. If you ever open this up, please be careful. Never handle electricity or work with electricity unless you absolutely know what you're doing. And even when you know what you're doing, you really need to employ quite a few safety procedures to prevent an electrical injury. Okay, so this right here is what's called the neutral bus bar. All of the circuits throughout your home or residence, they're all going to be wired into this bus bar. And the reason why everything is wired into there is because it's at 0 volts. It's connected to the pole transformer, so its 0 volts is with respect to the pole transformer. Okay, we'll talk about transformers at the end in a little more detail. Okay, we also have 2 bars. Okay, we have this conductive bar right here, which carries one of the hots, and another conductive bar right here, which carries the other hot. And the way that this is laid out is each of these breakers alternate. Like this one and this one are connected to the red wire to the transformer. This one, and this one are in the black. So these two are connected to the black, and then these two are connected to the red. Okay, and we can see here that basically our energy is coming in here. There's usually a double throw breaker right here that then distributes each of the hots to these 2 conductive bars. Your breakers, your circuit breakers, will then click onto those. It will actually secure themselves onto that conductive bar, and then we'll attach a wire to that to go out to each individual circuit. Okay, so for instance, most of what gets sent out, like here's a 15 amp circuit, you notice that it's hooked only to one breaker because it only has the one hot wire. Okay, that would be connected to most things that don't use a lot of power. But here we have a 240 volt circuit, and notice that what actually happens here is, they don't show this very well, but these 2 breakers are locked together. So when one throws, it takes both hot wires off. So that's the reason why we alternate red, black, because if we're going to use both circuit breakers, if we're going to use the whole, oops, that's not the tool I wanted. If you want to use the whole 240 volts, then we need both hots next to one another, thus the need to alternate. Okay. The other thing that you see here is a separate bar, and this is another bar. This is what is known as the grounding bus bar. And remember, when we wire different things up, we have a hot, a neutral, and a ground. This bar right here is connected directly to the ground. There's actually a metal rod that goes into the ground, and that's wired directly to the ground, which is held to be 0 volts. Now, if this is your main breaker box, okay, or this is the main breaker box in the building, what they will oftentimes do is connect the ground to the neutral bus, okay? In any system, you only want to do this once. And the reason why is because sometimes this panel will power another panel, but that'll have its own circuit breakers. If we connect the ground and neutral in every circuit breaker box, you're going to have some of the ground wires, which aren't designed to do this, take back some of the power on the neutral. Okay, so you don't, it's called bonding. You only want to bond one of these boxes. But again, this really shows you, what happens when you overpower a, an outlet or some part of the home. What'll happen here is you'll draw too much current through one of these wires, okay? That'll heat up a bimetallic strip in one of these things, and it'll cause the switch to throw. Or in the worst case scenario, you have a short, that'll also cause it to close, okay? If you ever have a circuit breaker, reset like that, or disconnect would be the proper word. Always try to resolve the situation before throwing that switch again, because if you're overloading the circuit, you need to take some load off. If it's a short, well, you better repair that or you're going to have a fire. Okay. But again, if you ever have any difficulty and you don't understand the electrical system, okay, calling an electrician, even though it can be expensive, is really the safest way to go about this, because you're talking about, when you have an energized box like this, you're talking about a tremendous amount of power that can cause a very significant, possibly life-threatening injury if you're not careful. And better to pay an electrician and be safe than do this yourself and receive a significant injury. Okay, so that is the home electricity and why we call it 120 VAC and 240 VAC.